Welcome to our N3AS seminar. Today we are very pleased to have Professor Anne Green from University of Nottingham, UK. She will talk about primordial black holes as a dark matter candidate. Over to you, Professor Green.
Okay, thank you. So in the US Cosmic Visions report in 2017, there was an overview of dark matter over a wide range of mass scales. And here we have right on the far right, black holes in a tiny mass range with one potential method of probing them. Whereas in fact, as I'm going to tell you in the next sort of 20-25 minutes, the mass of primordial black holes as a dark matter candidate can vary from asteroid masses right up to many times the mass of the sun. And then there are, in fact, a wide range of methods for probing them. So in a little bit more detail, I'm going to start by talking about the motivation for primordial black holes as dark matter and a little bit about the history. I'm then going to talk about how they can form and then about the observational constraints on their abundance. And then finally, if I've got time, I'll wrap up by briefly mentioning what I think are the important open questions in the field. And a lot of this is going to be based on an updated version of a review paper I wrote with Bradley Kavanagh a couple of years ago. There's also another review paper, one of many, by Bernard Carr, who is possibly the world expert on primordial black holes. And if you're interested in future prospects, then there was a SNOMAS white paper which focused on this topic. So to start with, what are primordial black holes? They're black holes that might form from overdensities in the early universe, by which I mean before nucleosynthesis, so the sort of first fraction of a second. And because they form so early, they're non-baryonic, which is one of the key requirements for a good dark matter candidate. Famously, they are thought to evaporate, probably, but there's been some debate about this recently, via emitting Hawking radiation. However, the lifetime is longer than the age of the universe if the mass is greater than about 10 to the 15 grams, which for context is roughly the mass of a mountain. So provided they're more massive than 10 to the 15 grams, they're stable, which is also a requirement for a good dark matter candidate. They're very different to the many other dark matter candidates that are typically considered, things like WIMPs, axions, sterile neutrinos, in that they're not a new particle. And sometimes people say that that means they have the advantage that they don't require beyond the standard model of physics. However, typically to produce the large overdensities you need to form them, you do need some sort of beyond the standard model physics, such as inflation. And I'll talk about that more in a little bit. So first, not long after Stephen Hawking sort of realised that primordial black holes could exist, it was realised that they were actually a cold dark matter candidate. And there was a first wave of interest in this back in the late 1990s. At that time, the Macho collaboration was seeing an excess of microlensing events towards the Large Magellanic Cloud, more events than could be explained based on the stars we know exist. And it was proposed that those microlensing events could be due to solar mass primordial black holes, making up about half the dark matter in the Milky Way. With subsequent surveys, that sort of observation went away somewhat. However, there was an important paper written at that time by Nakamura et al., and they pointed out that if a significant fraction of the dark matter is in the form of primordial black holes, then primordial black hole binaries would form at early times, just for the fact that you get some of them in close proximity, and then a close encounter with a third primordial black hole would lead to angular momentum exchange and hence the formation of a sort of gravitationally bound binary. And if those binaries survive to the present day, they pointed out that gravitational waves from their coalescence would be detectable by LIGO. Now, I must admit that I was aware of that paper at the time, but completely forgot about it. However, in early 2016, LIGO Virgo announced the discovery of gravitational waves from mergers of slightly more massive black holes, tens of solar masses. And rapidly after that, an announcement, there were a series of papers which were sort of making the proposal that some, at least, of those black holes could be primordial black holes rather than astrophysical black holes formed at the end of the lifetime of massive stars. And could those primordial black holes also be a significant component of the dark matter? So hence solving two problems in one go. And that has led to a second, much larger wave of interest in primordial black holes. And we've now reached the point there are sort of 300 or 400 papers being written every year on the topic. So first up, I'll go into a bit more detail about the formation of primordial black holes. Any situation where you get an overdensity such that it sort of falls within its Schwarzschild radius, you then get a black hole formed. The most popular and probably most minimal mechanism is the collapse of large density perturbations during radiation domination. And these are the same density perturbations that form galaxies and galaxy clusters, but on much shorter length scales. And as we'll see in a moment, they have to have much larger amplitude. And in this case, if a particular region is sufficiently overdense, then shortly after horizon entry, i.e. it becomes comparable to the observable universe, gravity overcomes pressure and it collapses to form a black hole. So this is the mechanism that most work is focused on and which I'm going to focus on today. However, there are various other mechanisms that I've listed on the slide. So the original calculation of the requirements for the formation of a primordial black hole and its properties go back to Bernard Carr in the 1970s. There's been lots of work refining these calculations, and those refinements are very important if you want to do detailed calculations. However, this zero order analysis does capture the key physics quite well. And so firstly, we have the criteria for PBH formation, which is usually phrased in terms of the density contrast, i.e. how big an overdensity is relative to the background density at the time it enters the horizon. And if that density contrast is bigger than a critical value, which is of order the equation of state parameter W, which is a third during radiation domination, then that fluctuation will collapse and form a primordial black hole with mass which is roughly equal to the horizon mass. And the mass within the horizon grows with time. The lightest black holes that won't have evaporated by the present day will be formed a tiny fraction of a second after the Big Bang, whereas solar mass ones will be formed around the time of the QCD phase transition. Subsequent work has shown that actually the threshold depends on the shape of the perturbation, which in turn depends on the power spectrum of the perturbations, but this works as a sort of order of magnitude calculation. We can then calculate the initial mass fraction of PBHs. It's typically called beta, and that's the fraction of the universe which is in regions which are dense enough to collapse to form a PBH. So you take the probability distribution of your density contrast on a particular scale specified by the horizon mass and integrate it from the threshold value up to infinity. And if you assume a Gaussian probability distribution, and I'll come back to that assumption later on, what you get is a complementary error function, which is essentially just the integral of over the tail of the Gaussian. And this quantity sigma is the width of that Gaussian, i.e. the typical size of the fluctuations, and it's called the mass variance. And so I've got a cartoon here where I've got my Gaussian probability distribution with width sigma, and the primordial black holes formed from the rare large fluctuations in the tail of the distribution. As we're going to see on the next slide, though, beta, the initial mass fraction, has to be very small. So in fact, we require that the mass variance sigma is much less than the threshold. We've got a very narrow distribution. And in this case, the complementary error function can be written in terms of an exponential. So what we're seeing here is you've got an exponential dependence on the size of the fluctuations in terms of how many primordial black holes you form. The next thing we want to do is connect the initial abundance to their abundance today, as in how much of the dark matter they'd make up. And a key thing here is that they form during radiation domination. And during radiation domination, the total density dilutes as a to the -4. However, the primordial black holes are matter, so their density only dilutes as a cubed. So the fraction of the density they make up during radiation domination grows with time. And this is what this plot here shows. We've got the radiation density in red and the PBH density in blue, going from radiation domination in the early universe through to matter domination at later times. And so the fraction of the dark matter that the PBHs makes up grows and then becomes constant during matter domination. And so you can go back from today to the time they form. And very roughly, we get this relationship between the initial mass fraction beta and the fraction of dark matter in the form of primordial black holes. And so if you wanted all of the dark matter to be in solar mass black holes, they'd initially have to make up 10 to the minus 9 of the universe. And the lighter primordial black holes form earlier, so their initial mass fraction would have to be even smaller. We know the amplitude of the primordial perturbations on CMB scales. It's been measured to be of order 10 to the minus 5. So one thing we can see already is that if the primordial perturbations are close to scale invariant, i.e. the same amplitude on all scales, then in fact the number of primordial black holes formed will be completely negligible. So if we take our expression for the initial mass fraction beta as an error function, and we put that mass variance of 10 to the minus 5 in, we get something absolutely tiny. Reversing the calculation, if we want to have F, the fraction of dark matter today, to be all primordial black holes, we can see that sigma, its square, must be of order 0.01. So to form an interesting number of primordial black holes, the amplitude of the primordial perturbations has to be significantly larger on small scales than it is on cosmological scales. And this plot here shows the power spectrum of the curvature perturbation, which is roughly equal to the mass variance squared, as a function on the bottom axis of our co-moving wave number k. But the more interesting thing in this context is in terms of the horizon mass, which is roughly equal to the primordial black hole mass. So over on the left, we have cosmological scales, and the regions that are shaded are excluded. So in fact, we've got a very precise measurement from Planck and then a less precise one from the Lyman alpha forest. And this line horizontally up here, that's roughly the amplitude that's required for all of the dark matter to be primordial black holes. So you have to grow your power spectrum from many orders of magnitude from its value on cosmological scales to cross this line at whatever sort of scale you want your primordial black holes to have that mass. There are also various other constraints, though, on the primordial power spectrum. For instance, large density perturbations would lead to spectral distortions of the CMB, shown in green. And they would also generate large tensor perturbations that could be detected, for instance, by pulsar timing arrays. And so, again, the current constraints are shown as shaded regions, and the potential future constraints are showed as dashed regions. So you can see that this is really getting you're going to have to grow your power spectrum and in the future, at least, avoid these regions that are constrained or probed by other observations. There are a few important deviations from the simple scenario I've talked about that I'll mention briefly. The first of these is a phenomenon called critical collapse. And black holes don't form with mass exactly equal to the horizon mass. The mass depends on the size of the fluctuation from which it forms as this power law. And this is something that's been verified by numerical simulations. And so the important point here is that even if all the primordial black holes form at the same time, they have a range of masses, i.e. we don't expect the mass function to be a delta function. Another important thing is that in my simple calculation, I assumed the probability distribution of the fluctuations was Gaussian. Since they're being formed from the rare large fluctuations in the tail of the distribution, if you change the shape of that tail, you can significantly affect the primordial black hole abundance. And that was something that was realized back in the 1990s. More recently, it's been realized that actually the distribution is inevitably Gaussian. The quantity that matters for PBH formation is the density perturbations. And so even if the sort of underlying quantity, the curvature perturbation, is Gaussian, it turns out the relationship between curvature and density perturbations is nonlinear. So even if your curvature perturbations are Gaussian, which I'll tell you later, they may well not be, the density perturbations will inevitably be non-Gaussian. So we know that non-Gaussianity is important and is going to affect calculations of the abundance of primordial black holes. So we think that the primordial perturbations are generated by inflation. In a moment, I'm going to talk about what you have to do in inflation models to produce large primordial black hole forming perturbations. But first, a brief reminder of what inflation is. It's a postulated period of accelerated expansion in the early universe proposed to solve various problems with the standard Big Bang, and it's usually driven by a scalar field rolling slowly down its potential. And quantum fluctuations in that scalar field generate curvature and density perturbations. And the scale dependence of those perturbations, i.e. how their amplitude varies, depends on the shape of the potential. And so we've got a simple example here. Our field evolves slowly down the potential. Inflation happens until it gets too steep, at which point inflation stops. Large-scale structure and CMB perturbations are generated over a relatively small range of the potential, whereas primordial black holes could potentially form from perturbations over a much wider range of the potential. And in the slow roll approximation, the mass variance squared, i.e. the typical size of the fluctuation squared, is given by this approximation here, where V is the potential and V prime is its slope. So what sort of things do we need to do in inflation models to produce large perturbations? So if we take this expression from the previous slide, you can see that if V prime becomes small, sigma is going to become large. And so it was realized in the 1990s that, for instance, having an inflation model with a plateau in the potential would generate large perturbations from which you could form an interesting number of primordial black holes. However, there is a caution here that the limit of V prime goes to 0 is actually what's called ultra slow roll, which slightly confusingly isn't slow roll. It violates some of the slow roll approximations. And in that case, this expression isn't accurate. You have to do numerical calculations. And as I'll mention briefly later on, ultra slow roll has an important effect on the probability distribution of the fluctuations. So the things that an inflation model has to do to produce primordial black holes and satisfy all other existing observations is, firstly, you have to match the measured power spectrum, both its amplitude and scale dependence on cosmological scales. You then have to increase the amplitude of the perturbations by several orders of magnitude on some smaller scale, and then you have to have inflation ending. The simplest inflation models are just driven by a single field, and it turns out to be very difficult to satisfy all three of those criteria in this case. And on the left, we've got a very fine-tuned potential that does that. The green shaded region corresponds to CMB and large-scale structure scales. We then have inserted in this region that's zoomed into a tiny little dip in the potential, with the idea being that the field gets slowed right down, but that it makes it over the subsequent peak so that the potential can then become steep so that inflation ends. So you can do it, but you really do have to fine-tune your potential. And on the right, we've got the corresponding primordial power spectrum, as I showed you before, and the numerical calculations, the accurate ones are the red lines. So they're matching the CMB scale observations, and then you get this peak, which takes you up to the amplitude you need to reach to form an interesting number of primordial black holes. So you can do it in single field models, but they have to be fine-tuned. So it's somewhat easier in multi-field models where you can decouple at least two of these three requirements. And an example which goes back to the 1990s is hybrid inflation with what's called a mild waterfall transition. And so in this case, the potential is as given on the left. Initially, the field slow rolls down this local minimum here. You reach a point where that's no longer a minimum. You've got these global minima here, and the field undergoes a phase transition. And if that phase transition occurs not too fast and not too slow, the quantum fluctuations during it can be large. And in this case, you will get this broad peak in the primordial power spectrum on the right. There are various other models that people have introduced which do produce large primordial black hole forming perturbations, and I've sort of referenced a couple of reviews there if you're interested. However, I think the thing to bear in mind here is there are many, many hundreds of different inflation models, and it's only a subset of them in which you can form an interesting number of primordial black holes. So then moving on to the observational constraints, there are an awful lot of them, so I won't go through them in detail, but if you've got any questions, I do have backup slides on them. So this plot is made by Bradley Kavanagh's PBH bounds code, which is publicly available, and it shows the constraints on the fraction of the dark matter in the form of primordial black holes as a function of their mass in solar masses on the bottom axis and grams on the top axis. Starting on the left, we have evaporation constraints. Anything lighter than 10 to the 15 grams will have evaporated away by today, but the slightly heavier ones, up to about 10 to the 17 grams, will have started evaporating and producing, for instance, MEV gamma rays at a flux which exceeds observation. So you've got these really very tight constraints on very light primordial black holes. We've then got this asteroid mass window, which is very hard to probe, and I'll talk about ways of potentially doing that later on. We then have very tight constraints across a wide range of masses in blue from microlensing, and in particular, stellar microlensing is very powerful, that when a compact object passes between us and a star, its brightness is temporarily magnified. And there have been various collaborations looking for these events either on short timescales or on very long timescales. And whilst there's been a handful of events observed, there's not been anywhere near as many as would be expected if all of the dark matter in the Milky Way's halo was primordial black holes. We then go up to sort of around the solar mass, and in purple, we actually have gravitational wave constraints. It turns out that if all of the dark matter was in the form of primordial black holes, you'd actually have several orders of magnitude more merger events than observed by LIGO Virgo. So providing our understanding of how these binaries evolve is correct, then in fact, those observations place a constraint on the abundance of primordial black holes. Moving to slightly more massive primordial black holes, in red, we've got accretion constraints. And what happens here is gas gets accreted onto the primordial black hole, and then you get emission, which could, for instance, change the thermal history of the universe and hence affect the CMB, or at the present day, they would be acting as X-ray or radio point sources that aren't observed. And so these place very tight constraints on very heavy primordial black holes. And similarly, once you go up to things weighing tens or 100 times what the sun does, these massive objects would just wreak havoc in dwarf galaxies or even in the Milky Way by sort of destroying wide binary stars. There is just one specific constraint I wanted to mention because this paper, which I'm highlighting here, came out this week, and I was quite excited by this. So this is new microlensing constraints from, I'm not sure if it's Ogle or Ogle, I'm never quite sure how to pronounce it, but these new constraints are in red. The previous constraints are as sort of solid grey lines. And so up until 2 years ago, the sensitivity of microlensing was sort of out to this point here. So you were just going to a few times the solar mass. 2 years ago, there was some neat work combining data from Macho and Eros, which pushed the sensitivity out to about 10 to the 3 solar masses. And then what's happened in the last week is those constraints are now going out to even higher masses and are much more sensitive. So it really looks like there can't be a significant population of solar or multi-solar mass black holes or any other compact object in the halo of the Milky Way. So coming back to our constraint plot, it seems that multi-solar mass primordial black holes, the ones that people got excited about because of the LIGO Virgo events, they can't make up all of the dark matter. Now, obviously, these constraints all have assumptions, and I can talk about some of those in more detail later if you want. However, it seems very implausible to me that all the constraints would shift in different ways to open up a region of white space somewhere here where all of the dark matter could be primordial black holes. However, there is this window down here with these hard to probe asteroid mass primordial black holes. I think, yeah, I'll just mention this very briefly. So all of these plots I've showed you so far assume a simple delta function mass function, i.e. all the black holes have the same mass, whereas I've told you that actually we don't expect that to be the case. We actually expect the mass function to have some spread. The plot on the left is what I've shown you before, just a slightly different version. The plot on the right is what you expect for a log normal mass function, which is a reasonable but not great approximation to the mass functions that people find. And what happens is the constraints get smeared out. So if we, for instance, look at one of these microlensing constraints in blue, the tightest point gets weaker as you go from the delta function to the extended mass function, but it then applies over a wider range of masses. So the upshot is that collectively the constraints are more powerful for realistic extended mass functions. However, you still have some region of masses where asteroid mass primordial black holes could make up all of the dark matter. I will skip that more detailed plot so that I have just in the last 5 minutes time to sort of talk about what I think the important open questions are. So the obvious one is how to probe these asteroid mass primordial black holes. So this plot now zooms into that region. The currently constrained regions from evaporation in orange and stellar microlensing in blue. And then the dashed lines show what you might hope to be able to do with improved versions of those observations. And the problem is that the evaporation goes proportional, I think, to the mass squared. So even a much bigger detector doesn't get you much improvement with the gamma rays. And with microlensing, it turns out there are fundamental limitations because of the size of the black holes being comparable to the wavelength of light, which means it's difficult to press microlensing down below 10 to the 22 grams. So to get into this asteroid mass region, we're going to need new ideas. And so, for instance, the things people have talked about are femtolensing of gamma ray bursts, lensing parallax of gamma ray bursts, which is when you observe them with two different satellites and one line of sight would be lensed and the other wouldn't, and also microlensing of X-ray pulsars. And by using much shorter wavelengths in these three cases, you're then able to get around these limitations which affect the stellar microlensing. Another big open question is exactly what the probability distribution of the density perturbations is, in particular in these ultra slow roll inflation models, which are what you need in single field inflation to produce the large fluctuations you need to form an interesting number of primordial black holes. And when you get to these sort of plateaus or in the potential, stochastic effects are very important. And it looks, they can to some extent end up with a probability distribution which is exponential rather than Gaussian. And so this would obviously have a very important effect on your prediction of the abundance of primordial black holes you form for a given potential. It's a really complicated problem, though. There are lots of people working on this, different aspects of it, including sort of Swagat Mishra, who's a postdoc with myself and Ed Copeland at Nottingham. And so there are lots of people working on this, and hopefully over the next few years, we'll get this one figured out. I'll skip that as well. And the final thing I'd like to mention is clustering. This is potentially extremely important because it would affect the rate at which the binaries would merge. And it was realized in the 1990s that if a large fraction of the dark matter is primordial black holes, then you will get clusters of primordial black holes formed shortly after matter radiation equality. And that's because they're discrete objects. You get Poisson fluctuations in their distribution, and just some areas would end up having more than average number of primordial black holes, and hence a cluster would form. And this is a result from some simulations by Derek Inman and Yassin Ali Hamoud of showing the primordial black hole distribution at a redshift of about 100. So you're seeing these clusters forming much earlier than structures would form for particle dark matter. The trouble is the evolution of those clusters as they merge together to form bigger sort of dwarf galaxies and Milky Way-like galaxies, that's a really challenging open problem. So the important question is, could this change the constraints I showed you before? And so, for instance, various people, including myself and a PhD student, have looked at the effect on the microlensing constraints. And for the clusters that form from Gaussian density perturbations, then it turns out the change is relatively small. Non-Gaussianity, which we expect, could lead to more compact clusters, and in which case there you could have the cluster as a whole acting as a lens rather than the individual primordial black holes within it. So in that case, the microlensing constraints would be weakened, However, people have looked into this and showed that other constraints from gravitational waves and dynamical constraints, they will get tighter. So it's not that your constraints can magically part to allow all of the dark matter to be in heavily clustered primordial black holes. The constraints shift around, but you still sort of can't have all the dark matter being primordial black holes in the solar mass region. So since I'm coming up on half an hour, I think what I'll probably do is just leave my summary slide up so you can read it, and so happy to answer any questions that anyone has.
Thank you, Professor Green, for the very nice talk. So people can raise their hand to ask questions. Okay, I can see various hands. Okay, so Susan, can you please unmute yourself?
Thank you very much for a nice talk. I have a question about your early mention of the Nakamura et al. Paper, where they remarked you'd have gravitational waves from primordial black hole mergers. But I guess my question is that given that it's so that the primordial black hole formation mechanism naturally comes from these rare large fluctuations in density, could we not expect gravitational waves from their formation in and of itself, and therefore there is some sensitivity floor that might be correlated with these objects as a substantial fraction of the dark matter? I don't know if it would be an interesting constraint, but it strikes me that it could be a constraint, and I was wondering if you have any thoughts about it.
Yeah, no, this is a good question. So for the ones which form by this popular mechanism, the collapse of density perturbations, I think it's fairly commonly agreed that that process does not in itself produce gravitational waves. However, there is, as I mentioned in passing, this thing that large density perturbations would induce the formation of gravitational waves. So there is sort of at much later times. And then also what I sort of haven't gone into detail here, and this is actually one of the things that's on my to-do list, is these other mechanisms. Given that you're requiring quite large overdensities and in some sense quite violent processes, it really does seem plausible that there would be a fingerprint of these processes also in gravitational waves. I mean, for instance, it's well known that cosmic string loops would also generate gravitational waves. It's just how the two things come together.
So wonderful. One could expect some future forecast of how the various mechanisms might imply a floor of stochastic background gravitational radiation that we can go over, allow us to constrain the different possibilities as our detectors improve.
I think so, and it just requires the difficult theoretical calculations to be done.
Oh, okay. Well, thank you very much.
Thank you, Susan. Serut, can you please unmute yourself?
Thank you for the wonderful talk. I'm not at all familiar with these multi-field inflation models. Can you just briefly say, are there motivations for them apart from trying to produce primordial black holes?
Oh, so I mean, here I'm very much an astroparticle theorist rather than a particle theorist. So I do know, so for instance, back in the 1990s, when people were initially coming up with these hybrid inflation models, there was sort of some motivation for supersymmetry theories, but I think it's, in general, it's the sort of thing that you can embed your inflation model in fundamental theories, but I would say that it's not that these models are coming out of fundamental theory in any way.
Okay, thanks.
George, can you please unmute yourself?
Thank you, Anne, for the great talk and the great overview. So Susan partially answered, I asked my question, but the question really revolves around this. You know, if I want to make larger primordial black holes, I don't really care so much about what fraction of the dark matter they are. It's just interesting to make larger black holes. So that's one, one issue. And then to that issue, I mean, anisotropies in the ultra low frequency, the nanohertz band gravitational wave spectrum might give you some indication of isotropy or anisotropy in that background. Are there, and I think one of your slides alluded to that. Can you expand on that?
Not much. So, I mean, obviously, I've truncated my limit plot here at about 10 to the 3 solar masses, very much because I'm interested in them being dark matter. And so my credulity bound is that dwarf galaxies exist. They have 10 to the 7 solar masses. So my plot isn't going sort of out beyond what's ruled out there. However, Bernard Carr and collaborators, their equivalent plots go out to 10 to the 11, 10 to the 12 solar masses. And indeed, you could form such massive primordial black holes, and they could make up a small fraction of the universe and have potentially observable consequences. And so people, for instance, are interested in them as potentially seeds for supermassive black holes.
Exactly.
In terms of, gravitational wave signals, let me actually go back to my plot and have a look. Right, so there we're getting into the region where actually CMB spectral distortions are. Yeah, so what I can't do off the top of my head is the right calculation of an exponential, as in if this green region, what does the bottom of that correspond to in terms of fraction of the universe in black holes? And I'm not sure. It would be something subdominant, but that of course could still be interesting.
Yeah. Okay, thank you.
Stephen, can you please unmute yourself?
Yeah, so I was just wondering if we have some observation of a black hole, whether it's electromagnetic or gravitational wave, I mean, even if we know the mass, is there any way to figure out if it's a primordial black hole or not?
So, I mean, I guess the obvious one is if it's less than Chandrasekhar mass. So that's the one where you would go, yes, this has to be primordial. Otherwise, I'm not aware of anything on a case-by-case basis, but you could, for instance, distinguish possibly populations of primordial black holes from populations of astrophysical black holes. And in particular, for this mechanism, the collapse of large density perturbations that I've talked about for forming them, they would typically have smaller spins. So people are looking at LIGO Virgo data. Can you disentangle different populations of black holes, primordial and astrophysical? So for things solar mass and upwards on a case-by-case basis, I'm not aware of any way of doing it, but mass functions, spin distributions, that would be the way you go about it.
Okay, but regarding spin, I mean, first of all, LIGO is seeing low spin black holes, and I think there was a paper out of Italy, Paolo Pani, talking about that these primordial black holes would get spun up. So it seems like sort of anything goes if it's a massive black hole.
Yeah, I must admit, I'm finding there's so many papers being written on primordial black holes, it's becoming increasingly difficult to keep up with things. So, I mean, I think, yes, it is possible for a subdominant population of the LIGO Virgo black holes to be sort of primordial. But I think one of the difficulties there is good predictions, not just for the primordial black holes, but actually for the astrophysical ones. What's being fit to the data is phenomenological models. And so hence there's lots of trade-offs between exactly what you assume.
Right. Okay. Thank you.
Charles, can you please unmute yourself?
Thanks for a really nice talk. I wanted to ask about clustering for asteroid mass primordial black holes. Can that give you large binary populations? And searching for gravitational wave signals from asteroid mass binaries is a very, very different data analysis. It's essentially continuous gravitational waves rather than bursts.
No, those are all good questions to which I don't know the answers off the top of my head. So I guess naively, but I could be wrong, I'd expect clustering to be less significant for the smaller ones because they're smaller. The Poisson fluctuations would be smaller, but I could be wrong about that. Yeah, that's the thing I should think about.
Okay. Are there any other questions for Professor Green? I don't think so. Okay, so let's thank her again for this very wonderful seminar, and we will see each other. We will see everyone in 2 weeks from now.
Thank
Thank you
you.
very much.
Thank you, Professor Green, for this talk.
Thank you very much.
Thanks.
Bye-bye.
Thank you.